All right, welcome. In this video, I'm going to be working some examples of parametric equations, calculus problems related to them, slope, second derivative, some particle motion. Really, I'm working through BC Homework 10.1. Okay, so the first problem is if x equals t squared minus 1 and y is equal to 2e to the t, then what is dy dx equal to? So I'll have dy dt equaling 2e to the t and dx dt equaling 2t. Now we know that dy dx is dy dt over dx dt. So we're just going to say that that is 2e to the t divided by 2t. I think that one was on the notes packet, but that's okay. Still dy dx. All right, the next problem is going to ask us to find dy dx at t equals 1. Okay, so we can do that. I don't think that. We'll just take dy dx and then plug in t equals 1. So I've got, all right, so dy dt is going to be equal to 1/2, leave the inside the same, reduce the power by 1, and then multiply by the derivative of the inside. So that would be 1/2 of 3t plus 1 to the negative half multiplied by 3 chain. Okay. And then dx dt is going to be 3t squared minus 1. Okay. What I might do to make this a little easier, rather than like combining these into a single fraction and then plugging in, I'm going to plug in and then divide. It's going to be the same. So dy dt at t equals 1, that'd be like y prime of 1, is going to be 3/2 of 3 plus 1 is 4 to the negative half. That's 1 over the square root of 4. Okay, that's looking to me like 3/4. X prime of 1, that's going to be 3 minus 1 is equal to 2. So I could say that dy dx at the point where t is equal to 1 is going to be equal to 3/4 divided by 2, which is the same as 3 divided by 8. All right, now we're going to put it all together and write an equation of a tangent line. So I'm going to need a point and a slope, just like always, and I'm going to get the slope by finding dy dx at the point they're interested in, and saying at the point where t equals 1. So we can do that. We're going to find the point by plugging in t equals 1 into x and y. X equals 1 to the third plus 1 is 2, and y equals 1 plus 2, that's going to be equal to 3. Yes, I could be more specific and say 1 plus 1 is going to equal 2. All right, and then my slope, I'm going to need my derivatives, right? I'm going to have x prime equals 3t squared plus 1, and y prime equaling 4t to the third plus 4t. Okay. At t equals 1, I've got 3 and 1 is 4, and 4 and 4 is 8. So dy dx, being y prime divided by x prime, is going to be 8 divided by 4, and that's 2. So I'm going to go over here now, and I'm going to say, well, I've got my ingredients. I can write the equation of my tangent line, and it'll be y minus 3 equals 2 times x minus 2. And that's how we write a tangent line. All right, now number 4 is going to ask us for the second derivative. Now you need to remember the important formula for finding the second derivative. So that's second derivative y with respect to x both times is equal to the derivative of dy dx, which is going to depend on t, so we're going to take its derivative with respect to t, and then we're going to remember to divide by dx dt. Okay? And so I'm going to go over here, and I'm going to say, all right, well, I'm going to need y prime and x prime. Okay, so dy dx is going to be 3t squared divided by 2t. That's 3/2 of t. Then I feel like this is another one that was on the notes packet I've already done, but whatever. I'm going to say that the second derivative I'm going to get by taking the derivative of dy dx. So I'm taking the derivative of 3/2 t with respect to t, and I'll just get 3/2. Then I'm going to divide by x prime of t, which is 2t, and that's going to be a safe place for us to stop. Number 5 is going to be write an integral that represents the arc length. We know how to do that. Right, so they're telling us x equals sine of t squared and y equals 3 over e to the t. And so you need to remember that the length of a parametrically defined curve is going to be the integral from t1 to t2 of the square root of x prime of t squared plus y prime of t squared, integrated with respect to time. And so I'm going to need x prime and y prime, right? I'm going to say that, all right, well, really, I'm going to need to rewrite y. So I'm going to just say, all right, x equals sine of t squared. So x prime is going to equal 2t cosine of t squared. I need to use the chain rule here. Y is 3e to the negative t. So y prime will be negative 3e to the negative t. And then the problem said length of the curve between t equals 0 and t equals 2. So that length will equal the integral from 0 to 2 of the square root of dx dt squared. So that's going to be 2t cosine of t squared plus dy dt squared negative 3 negative t squared. All of that. Time. That's an integral that represents the arc length. All right, this next one's actually asking us to find the length. So I'm not going to write the formula again. I'm just going to start by taking my, derivatives to get f prime of t. That's going to be 1 over t squared plus 1 multiplied by 2t for the chain rule will be 2t over t squared plus 1. And the derivative of the second component would be 6t minus 1. Okay. At this point, what am I going to? Oh, I'm finding the length of the curve from t equals -1 to t equals 1. Okay, so the length of the curve is going to be, all right, if this is going to be x prime of t, and that's going to be y prime of t. We're going to be taking x prime of t squared plus y prime of t squared and taking the square root of that and integrating it from -1 to 1. So this length is going to equal the integral from -1 to 1 of 2t over t squared plus 1 squared plus 6t minus 1 squared, all square rooted and integrated with respect to time. Now, something's gone wrong with my document camera, so I'm not going to be showing you the actual steps of computing this, but I'm just typing it into the TI-84, just like always, using Math 9. I'm going to be in function mode, not in parametric mode, because you don't need to be in that mode to solve any of the problems. And I'm just typing in the square root of, I'm going to have to add a fraction bar. This is pretty bad. 2t, but instead of t, I'm using x. Because it doesn't matter what the variable of integration is. Kind of irrelevant. It computes it the same way. Plus then 6t minus 1 squared with respect to t. As t runs from -1 to 1. And let's see, 6.363. All right. Number 7 is consider the curve. All right, so x is e to the t and y is t e to the t. And find the slope of the line tangent to the curve at the point where x is equal to 3. All right. Well, you know what? I'm doing this one by hand. Evidently, you can use a calculator on it. I don't know what the idea is with using a calculator. I suppose, I don't know. Can't think of any good reason to use the calculator on this. So I'll just move forward without the calculator. Why? prime equals 1 e to the t plus t times the derivative of e to the t is going to be t. X prime is equal to 1 e to the t. So I want the slope of the tangent line, which is dy dx. Okay, so y prime over x prime. So, oh, okay. Yeah, I can do a little bit of this, right? I'm factoring out the e to the t from both terms, and I'm left with a 1 plus t. Okay, we're interested in the point where x equals 3. Oh, I know what it is. Yeah. So at the point where x equals 3, it's like, well, how do I find that, right? So I'm going to say e to the t equals 3. Fortunately, this is something I am able to solve by hand. And now I'll say that dy dx at the point where x is equal to 3 is equal to 1 plus t, which was the log of 3. That may have been what required these for calculator. I wouldn't say required because I was able to solve it without one. Before I have to pause real quick. Number 8, what values of t does this curve have a vertical tangent? We can do that. Why is t to the 4 plus 2t to the 2 minus 8t? Okay, a vertical tangent is going to be a place where x prime equals 0 while y prime is not 0. So I'm just going to take x prime. Okay, figure out where that equals 0. And that's going to be t times 3t minus 2. That's going to be t equals 0 and t equals 2/3. And I guess I just need to check against y prime to make sure it's not simultaneously 0, because that would be a problem for us. That would not be a place where there was a vertical tangent. So 4t to the 3rd plus 4t minus 8. Okay, 0 is definitely gonna pass. It's gonna have a vertical tangent. I mean, I can't see a world in which 4 times 8 over 27 plus 8/3 is 4t. Yeah, that's neither of these is going to cause y prime to equal 0. So I'll be satisfied. It'll work out fine. Both of these will be t coordinates where there's a vertical tangent. Okay, number 9 is going to be f being e to the negative t over 2 and cosine of t, and we're just going to find the second derivative. Yeah, so we're going to start by, I don't know, I might rewrite e to the negative t over 2. I had to read that far enough in the year where I don't ever have to do that again. I don't really know. If you're not sure what to do with that, we're going to call that e to the negative 1/2 t and cosine t. And then, okay, that means that f prime of t is going to be negative half e to the negative 1/2 t and negative sine t, and then we'll take the derivative of that to get f double prime. Okay. And I'm noticing that this one's got parentheses around it, not kind of the sharp, pointy ones. And it seems to me like I've seen both in College Board AP Calculus problems, right? I've seen ones where they just use parentheses, and the derivative of negative sine of t with respect to t is that's going to be negative cosine t. I've seen they just use parentheses like a point. Okay, so I guess my idea there, my message is that you need to be ready for both of them. Okay, so next question is asking about the concavity of a curve. Now we know that if we're trying to find the concavity of something, we need to find the second derivative of y with respect to x. And we also know how to find that. That's going to involve dy dx and dx dt. So I need to take y prime and x prime. Y prime is equaling 9t to the 2, and x prime is equaling 6t to the 1st. Okay, this is another one. It's not that exciting, but it's all right. I'll take not exciting over the really bad second derivative of y ones. You don't want to go there. Okay, so dy dx is going to be 9t squared over 6t. Well, that's going to be, what is that going to be? It's going to be 3/2 t to the 1st. meaning the second derivative is going to equal the derivative of dy dx, 3/2 again. Every time I've done one of these, it's been 3/2 in the numerator. Divide by dx dt is 6t. Okay, now, the only way that I'm going to have this fraction come back and be a negative number is if t is less than 0. Okay, so I'm going to say, as far as concave down, that's if and only if t is negative. But if t is less than 0, then that gives me that x is positive, right? Because I take a negative number and I square it, it's positive, multiplied by 3, so positive. And y is going to be negative because I take a negative number, I take that to the third power, it's going to be negative, multiplied by 3. 3 times is negative, and then subtract 5 more, it's going to be even more negative. So I'll have x is positive and y is negative. So over here, where x is positive and y is negative, that's quadrant 4. Okay, so I'll say that the curve is concave down in quadrant 4. All right, this is a type of problem I didn't think was going to be on this problem set, but it appears it is. Okay, we're moving along the curve y equals log x with a given x velocity. Okay, and we want to find the position of the particle at time t equals 1. So we're going to be able to do that. So we want to know the position at time t equals 1. So I can't figure out the position all in one go, but I can figure out the x coordinate position because I've got the derivative of x and I've got an initial condition. So I'm going to say that x of t equals 1 equals x of t equals 0 plus the integral from t equals 0 up to t equals 1 of x prime of t dt. Okay. So x of 0 is equal to 1. And x prime of t is t plus 1. Now, we could probably do this one with geometry, right? It would be like some kind of a trapezoid or something. But I think it's going to be easy enough that I'm just going to do it by hand. 1/2 t squared plus t as t runs from 0 to 1. Yeah. So this will be when t is 1, this will be 3/2. And when t is 0, it'll be 0. So that'll be 1 plus 3/2 is equal to 5/2. Okay, but it didn't just ask for the x coordinate of the object's position. It asked for the position of the object, of the particle. So, but the thing is, we can go all the way back up to the very beginning and say, okay, we're moving along the curve y equals log x. So at any point on the curve, on the path, if I've got the x coordinate, I can get the y coordinate by taking the log of the x coordinate. So I know that the position, maybe I'll even say it's the position vector at time t equals 1 is going to be x equals 5/2 and y is equal to the natural log of 5/2. Or you could say it's, at the point 5/2 and log of 5/2. That'll be 1. All right, number 12 is another motion question. Okay, the position is x equals t squared minus 1 and y equals t to the 4 minus 2t to the third, but we want to know the acceleration vector at time t equals 1. Okay, and we know that in this one-dimensional case, acceleration is the second derivative of position, and it's going to be the same thing in the vector value case. So I'm going to say, all right, well, my velocity vector is going to be x prime and y prime, which is going to be, I can take the derivative of t squared minus 1, that's 2t. And this derivative of y is going to be 4t to the third minus 6 times t to the 2. Okay. And then what else? Oh, yeah, I need the acceleration vector. That's what I wanted. Acceleration vector at time t equals 1. Yeah. Okay. And let's get that by taking the derivative again, which I think y'all are probably okay with, but It's going to be the vector 2 and 12t to the 2 minus 12t to the 1, indicating to me that at t equals 1, the acceleration vector is equal to 2 and 0. That's something we can do. 13 is another position velocity one. Write the acceleration of the vector in terms of t. I bet we can do that. Let's just say that velocity vector is going to be 2t, derivative of x, and the derivative of y is going to be 1 over 2t plus 3 multiplied by the derivative of 2t plus 3 with respect to t. And so I'll get that. Okay. Now I know if I'm going to have to take the derivative again, then I'm going to write this as 2 times 2t plus 3 to the negative first power. So I can use the power rule and then I guess eventually the chain rule. We just want the acceleration vector, and that's going to be 2 and negative 2 times that thing to the negative second power times the derivative of that thing. So it'll be times another 2. And that'll be good enough for us, right? We just want an expression for the acceleration. All right, here's another one. We want to find the acceleration vector at time t equals 1. It's not the most creative problem set ever, I know. We'll be all right. We can just take the derivative twice. Velocity vector is going to be 3t squared minus 1, and 3 times that thing squared times the derivative of that thing. And I might just rewrite that to make my next derivative taking a little easier. Yeah. So that the acceleration vector at time t is going to be 6t, and 12 times that thing to the first times the derivative of that thing. And if I want the acceleration at time t equals 1, I'm just going to plug in t equals 1. I get 6 there, and 2 minus 1 is 1, so 12 and 2, that's going to be 24. Oh, hold on a second. My pen has gone out. Yeah, there we go. Okay, we've done that one. Number 15 is going to be an up, down, left, and right type question, and this is good. I've seen a few multiple choice items that look like this before. All right, so they give us the position of the object, and they say at the point when x equals 1 and y equals 1. This is not too hard to figure out, right? What t gets you there. But I've seen ones where it's not as obvious. Okay, so you just stop, take a second to figure out what time value gets you to that position. It's usually not too hard of a time value, and then you proceed. So you take a second, you're like, all right, I know, this is when t equals 0. Okay, so we've got t equals 0, and we're going to need the velocity to tell you about which direction the object is moving. So x prime equals negative 1, and y prime equals 0 minus e to the negative t times negative 1 would be 0 plus e to the negative t. And, well, I'll say that my velocity vector at really whenever is going to be negative 1 and e to the negative t, which is negative 1 is always negative, and e to the negative t is always positive. So I can say that it's moving to the left because of the x-coordinate decreasing, and up because of the y-coordinate increasing. So I would conclude that it was going up and to the left. All right, and the last one for this problem set is going to be, determine if the curve determined by the vector-valued function r, which is 3 cosine t and 5 sine t, is concave up or concave down at the point where t is pi over 6. All right, well, this should be exciting, at the very least. So I'm ready to find dy dx. Y prime is going to be 5 cosine t, and x prime equals negative 3 sine t. meaning dy dx is -5/3. Cosine over sine is cotangent t. Okay, that means that the second derivative of y with respect to x both times is going to be the derivative of -5/3 cotangent t, so that'd be -5/3 times negative cosecant squared t divided by dx dt is -3 sine t. Okay. Now, I'm going to probably remind you of something your pre-calculus or your trigonometry teacher told you, is about, where are each of the types of functions positive. Okay, in this quadrant, all of them are positive. Over here, sine is positive and cosecant. Down here, tangent and cotangent are positive. And over here, cosine and regular secant are going to be positive. Right? We say, like, all my students take calculus, or at least college algebra. That's what I used to say when I taught pre-cal. And so what we need is that, okay, at pi over 6, I'm just telling you, like, hey, everything's positive. Pi over 6 is in the first quadrant. So all of these trig functions are going to be positive, meaning that I've got a positive number squared and a positive number when I'm computing sine t. So if I just, went over here and it's like, all right, -5/3, that's a negative number. Now, the thing about the negative cosecant squared t, it's like, wait, do I negative first and then square it? Or square it and then make it negative? And you've got to remember, it's exponents before multiplication by -1 in a PEMDAS world. So I do still have that negative before the cosecant squared t. And also think about it. I wouldn't write negative cosecant squared t if you're supposed to take a negative and then square it, because once you squared it, you wouldn't have negative anymore. So then over here, I've got -3, and that's a negative number. So all in all, I think I've got a positive divided by a negative, which is going to be equal to negative. So I'm going to conclude that the curve is concave down at t equals pi over 6. That's going to be all for this video. If you want to see me working the extra practice problems, well, I'm going to record that pretty soon, but I'm going to record it as a separate video. And, maybe I'll have it linked. Maybe you'll have to go looking for it. Either way, if you feel like you need more practice on the dy dx and second derivative of y with respect to x, yeah, a few algebraic problems should do. So happy practicing. Thanks for watching.